Hey, we have a really interesting looking integral here today from the MIT Integration Bee 2023. This was regular season problem 20. We have the integral from 1 to 100 of the floor x over 2 over the floor of x plus the ceiling x over 2 over the ceiling of x dx. Okay, a lot to deal with here with the floor and ceiling in the same integral. Now for a situation like this with the floor and ceiling, I usually like to break up the integral. So let's just try that a little bit to get some sense of it. So I'll start with an integral from just 1 to 2, just so that we're looking at an interval with a length of just 1, or a width of 1. Now what the floor function is going to do in this region between 1 and 2 is it's going to round us down, so it's going to take us down to 1. And then let's look at the ceiling over here. So the ceiling between 1 and 2 is just going to round us up to 2. And what you'll find is in each of our integrals, if we make it a length 1 like this, the floor is going to be the lower bound and the ceiling is going to be the upper bound. So if we look at the floor of x over 2 between 1 and 2, we're going to have values here of like 0.5 all the way up to 0.999. So the floor function is going to round us down, so this value is just going to be 0. And then if we take the same values from 0.5 to 0.999, when you divide our x values by 2, the ceiling is going to take us up 1, so this value is always going to be 1. But now of course we've got a 0 here, so we're going to just cancel that one off. And so we're just integrating a half. So let's just integrate this one while we have it here. So this is going to be 1/2 x integrated from 1 to 2. And this is just going to be 1 minus a half, or 1/2. And so like I said, this is the only one that has a 0 in it. I'm just going to add this to our full integral, but then change the bounds. So we're just going to be integrating this from 2 to 100 now. And we've kind of separated off this one case. Okay, so next we're going to evaluate from 2 to 3. And again, like I said, with the floor, that's going to give me the lower bound of 2. And then the ceiling is going to give me the upper bound of 3. If we look at values between 2 and 3 and we divide by 2, that's going to be between 1 and 1.5. Well, the floor is going to take me down to 1. And then similarly, when we have our values from 1 to 1.5, if we have the ceiling, that's going to take me up to 2. And then we'll just do the same thing from 3 to 4. So again, our floor is going to be the lower bound at 3, and then the ceiling is going to take me to the upper bound of 4. Between 3 and 4, if we divide by 2 and take the floor, we're going to be at 1 right here. And between 3 and 4, when we divide by 2, we get values between 1.5 and 2, so the ceiling is going to take me up to 2. And so instead of doing this 98 times, what I want to do is generalize this to kind of get a sense of how it's going to work for any interval. Okay, so what I wanted to do here is look at 2 adjacent intervals, just the way we had here with going from 2 to 3 and 3 to 4. So here we're going A to B and B to C. And I want to set this up where A is going to be even. I think we're going to find the even odd is important. And so then our B value is going to be odd. Of course, this is the same B right here, so this is also odd. And then our C value is going to be even. We know with the denominator, like the floor of X is going to be just our lower bound. So we're going to have an A here, and then we'll have a B here. And then the same thing over here, we're going to have our lower bound B, and then we're going to have our upper bound C. And then now for the floor of x over 2, we just want a formula in terms of a and b. And then we kind of saw from how this works that what we're going to need here is a over 2. And then for our ceiling of x over 2, it's just a little more complicated. It was the upper bound, but we had to add 1. So it would be like b plus 1 over 2 to express that. And then over here, it's going to be the same kind of thing. But again, the odd and even is kind of important. So for this value, for our floor of x over 2 between b and c, where b is odd, this is going to need to be b minus 1. We're taking it down 1 and dividing by 2. And then over here, this is going to be kind of like this value, where this ceiling is going to be c over 2. But then we can do a lot of simplifying with this. Like first of all, dividing a into a over 2, that's just going to be 1/2. And then here we can split this all up. We can divide the b in, so we can write it as b plus 1 over 2b. And then doing the same kind of thing over here, we have b minus 1 over 2b, and dividing this c in here is just going to give me 1/2. But now for this, I can actually write this as 2 fractions. I can write it as b over 2b plus 1 over 2b, but then that's going to give me another 1/2. And then we, of course, doing the same thing over here, dividing the 2b in, we can have 1/2 minus 1 over 2b. But then putting it all back together, I can take this 1/2 and add it to this 1/2, and we just get a 1 here. And doing the same here, this is 1/2. If I add it to this one, we get 1. So let me just rewrite this so we can clearly see what's happening. Okay, so here you can see we have quite a bit of simplification by just combining the fractions and just doing some arithmetic with it. And what I want to do now is I can break this into 2 integrals and break this into 2 integrals, so we have 4 integrals. So I'm just going to reorder it. I'm going to put these 1's together. So we're integrating from a to b of 1 dx. And then we'll take this one and integrating from b to c of 1 dx. And then from here, I'm just going to write in these 1, 2b integrals and split it up so we have 4 integrals. Okay, now here, this is really nice because we're going from a to b and b to c, I can actually combine these two and write this as going just from a to c of 1 dx. Now we can consolidate these two, but just to make it clear, I think I'm just going to integrate it out so we can see what's happening. That's probably the easiest way for me just to explain it. 1 over 2b is a constant value, so when I integrate that, we're going to have 1 over 2bx evaluated from b to a. And then here, same thing, we're going to have 1 over 2bx evaluated from b to c. And then I can just factor a 1 over 2b out. And then here we're going to have our bounds from b minus a. And then here when we evaluate, we're evaluating from c to b. But the thing is, the difference between a and b is just 1. And the difference between b and c is just 1. So this piece is 0. And so that means this whole thing is 0. So these two integrals together are 0. And so we can just cross that off and ignore it because none of that's going to matter. So now we're just left dealing with this integral of 1. We just need to figure out exactly how to line this up with our bounds, and then we can just integrate 1. Now remember, we said that a is going to be even. Also, we had c is even. So if we were to start writing these out, if we were starting at 2, our next even value would be 4. So we're saying we're integrating from 2 to 4 dx. And then we're integrating, let's say, from 4 to 6 of 1 dx. But the nice thing is, our upper bound, 100, is also even. So there's not going to be any extra pieces, right? When we add this all up, our last interval is just going to be 98 to 100, 1 dx. And so we can just take all these integrals and just smash them all together and put it back. So what we're going to end up with is we just need to evaluate this. We just need to integrate from 2 to 100 of 1 dx. So when we integrate this thing, we're just going to get x, and we're going to have to evaluate from 2 to 100. But that's just going to be 100 minus 2, or 98. And so this whole piece right here is 98, but we still have this 1/2. So all we need to do is we'll just add 98 and 1/2. And then if I get a common denominator and write this piece as 196 over 2, we get our final solution of just 197 over 2. So that's it. Pretty interesting problem from the MIT Integration Bee. We'll stop it there. Thanks everyone for watching. Have a great day.